So this lecture is on climate and soils. It's going to be a two-part lecture. First, I'll cover climate and how that affects geomorphology and surface processes on the planet. And then in the second part, we'll look at soils. So this first diagram here, this is showing carbon dioxide, methane, and delta D ratios as they change through time. So you have 400,000 years in the lower right and today in the lower left. These are proxies for global temperatures. So we have periods of higher temperature, with the most recent being about 120,000 years ago, and periods of lower temperature on the planet that we call ice ages. So we can also look at this in a little more detail in just the last 100,000 years. And even over the last 100,000 years, we have changes, with global temperatures rising and dropping. And currently, they are obviously warmer than they've been for quite a while, with the last ice age kind of being at a maximum at about 18,000 years ago, and we've been warming up since then. So the question then is, how do these climate changes affect the landscape and the surface processes? So there's several different ways that climate will affect the geomorphology. The first is, as climate changes, sea level changes. So a rise in sea level creates a rise in base level for any streams that are draining into the ocean. So this can change the dynamics of the fluvial system. So we're looking at the east coast here, where you can see a little bit more dramatic effects because it's a passive margin. You don't have high topography along the coast like we do on the west coast. Chesapeake Bay is a great example. That's right here and here on the image on the left. So if we look at the bathymetry of Chesapeake Bay, or the topography underneath the water, you can see these old river valleys and tributaries coming off of it. So in this area, rising sea level not only caused the streams to backfill with their own sediment due to a loss of stream power, but they even backfilled with seawater. I mean, sea level rose enough that it started to fill in what used to be a river valley. So we can see that in the topography underneath the water. Out in LA area, we've got a pretty low relief, kind of flat Los Angeles area plain, the LA basin and the Orange County basin here. So relatively minor changes in sea level can actually cause the shoreline to migrate great distances in or out. So you see this shelf offshore of Long Beach and Huntington Beach. So the last glacial maximum, the shore would have been quite a ways out here. And at 120,000 years ago, when sea level was higher than it was today, we would have had the shoreline farther in. Palos Verdes is a great place to see evidence of rising and falling sea level, because Palos Verdes was an island for much of the Quaternary, and we can see that because you've got these wave-cut notches, these marine terraces, and they're not only present along the coast, but they're also present on the inland side. So we can see that Palos Verdes was completely surrounded by water for some periods of time in the last throughout the Holocene and Pleistocene. Looking even more offshore, so now downtown LA is here, Long Beach is here, here's Palos Verdes. We can get an idea of what the topography looks like underneath the ocean out here. And we see we've got several islands that we call the Channel Islands: Catalina, San Clemente, Santa Cruz, Santa Rosa, San Miguel. And when sea level was lower, these islands would have been possibly connected with dry land, and maybe even connected to the mainland here in the Ventura area. If not, these channels are at least much smaller, not allowed animals and even people to migrate between these. So moving sea level up and down has a big effect on river systems and also just the geography of the area where the coastline is located. Changes in climate will also create changes in precipitation, which then changes the amount of water in a stream system. So remember from previous lectures that stream power will change with any change in the amount of water, which we discharge was in the equation representing the amount of water, sediment amount, the slope, which is again dictated by base level change of sea level going up and down. But adding more water, you can turn what might be a small stream into much larger streams, when you have wetter climate. And not only that, but the size of the stream might change, but also the dynamics of the stream might change. You might go from a meandering stream to a braided river, right? So big changes, and we can see evidence of this along the Orange County coast, which the second field trip will deal with. Precipitation changes also change vegetation. So there's a map of western North America. The different colors are representing different vegetation zones. So this is today. The red is sort of desert areas, and brown as well, and the more forested areas are shown in green. So if you look over at last glacial maximum 18,000 years ago, we see that the areas that were covered by forests were significantly larger. So even Southern California, we had large forests. So vegetation changes can then influence erosion of slopes. So the more vegetation you have, the more soil buildup you get. The root systems kind of allow soil to build up on the slopes. So here's a picture of the San Gabriel Mountains today. We have very thin soils, if at all. I mean, look at this picture. There is some soil on the slope, but there's places where bedrock is poking through. And the vegetation is obviously pretty dry, what we call chaparral. During the last ice age, the San Gabriel Mountains might have looked more like this. This picture is actually from western Norway, but something like Oregon or Washington that we see today, which big conifer forests and much wetter. Those vegetation changes and precipitation changes dictate the amount and degree of weathering of the rock as well. So when you have drier conditions, your weathering generally slows down. So you're producing soil at a slower rate, and you are denudating the landscape generally at a slower rate. And then changes from wet to dry can have big, drastic, quick effects on the landscape. So topography like this that you see out in Joshua Tree, where you have these kind of rock mounds exposed, well, these were originally formed through chemical weathering underneath the ground surface. So the ground surface would have been up here, and this would have been surrounded by degraded material, soil. And then as the climate changed, the vegetation died off, all this soil is easily erodible, and it just gets taken away, and you're left with these core stones sticking out. These were just more resistant, but they were originally in the soil profile. And we'll talk about that in a few minutes here. Another major change is changes in glaciation. So in Southern California, we really don't see a whole lot of impact from this. There are evidence of glaciers in the San Bernardino Mountains, but most of Southern California was not glaciated. But other parts of North America, there's big changes due to advancement or retreat in glaciers, and big changes in the geomorphology associated with that. This picture is from eastern Greenland, and you can see this is a big glacial valley. The glacier today is way up here, so it kind of terminates there, and you've got this braided stream coming out. But you can tell just by the color of the rock that the area up here has been weathering for much longer than this area, this lighter area, because this was covered by ice. So we see the glacier is retreating through time and exposing relatively unweathered rock as that ice retreats. Just a side note, this is another picture from eastern Greenland, kind of an interesting little channel. So this is a small, what at one time would have been a river channel, but these little cobbles that are in here, this is very flat. When you're walking across it, it was almost like walking across a cobblestone street. The top of these rocks are flat, and they've been planed off by glacial ice that once covered this little stream. But if you take one of these rocks out and flip it over, the underneath side is perfectly rounded. So these were actually deposited by fluvial processes in between a glacial period. But then small glacier developed and came down this drainage and more or less planed off, eroded off these rounded cobbles. And then as it retreated, you're now able to walk across it. So just these cobbles are recording a period of fluvial, changing to glacial, and now back to more fluvial. Okay, so you can see these changes on small scales like this and big scales of entire mountain range or continent. So one other thing to keep in mind with these climatic changes is they're relatively fast in terms of Earth's history, and the geomorphology of the landscape takes time to adapt to the new climate. So in many parts of the world, landscapes that we're looking at might be relict. In other words, they're shaped by processes that are no longer active. The Sierra Nevada and Yosemite are a great example of this. So Yosemite was carved by glaciers, but those glaciers have since melted, and it's nothing but streams coming down through here. This confused early geologists for a long time. In fact, the first geologists in the Sierra Nevada assumed that Yosemite Valley was formed by some cataclysmic event where the valley just dropped out, bounded by big faults. And it was actually John Muir that pointed out that this was glacially derived, and the geologists at the time totally made fun of him. But later he was proved to be right, that there were actually glaciers in Yosemite Valley. Okay, so this is important to keep in mind, that the landscapes that we see today may have some relict features from an environment or a climate that is not present today. Okay, so that wraps up the climate part of the lecture, and I'm going to move on quickly now to talking about weathering and soils. Another picture from the Joshua Tree area, because I think these rock mounds and outcrops are a really good example of the story of weathering and then interacting with climate. So these again were formed by weathering underground, and then as climate dried out, all that soil that was developed just got washed away, and we were left with these remnant solid rocks that were in the soil. So just a quick side here, we're going to talk about soil formation and how you characterize it and look at it more from a scientific point of view. From a practical point of view, though, soils are really important, because much of what we build on the planet is soil. It is unconsolidated material, and getting the exact density and stability is crucial for safety and in constructing buildings. So there's a large number of geologists on the planet that are engaged in creating stable environments to build, whether that's on solid rock in some places, but in many places it's on unconsolidated soil. So how do we form soil? Soil, first, what is it? It's just decomposed rock material. So it's generally a combination of mineral material as well as some organic material. And so we're going to look at the process of going from solid rock to soil, and this is what we call weathering, breaking up of rock. So there's two main types of weathering. There's chemical weathering and physical weathering. So we'll look at chemical weathering first. Chemical weathering is a breakdown of rock by chemical processes. And there's a couple different processes that occur, but this happens when rocks are exposed to the atmosphere and or water. So we don't really have a whole lot of chemical weathering going on at 1 kilometer depth. It's not until you get closer to the surface that rocks begin to weather like this. So one way is from dissolution. Dissolution is minerals dissolving in water. So salt is an example. Water will pull salt apart. And so we fundamentally change the rock by doing that. You're pulling pieces apart. At the other side, you can then precipitate this material somewhere else. So these stalactites in this cave are a good example of dissolution. So some material actually dissolves in the water and it can be transported out of the system or possibly deposited somewhere else. A second type of chemical weathering is what we call hydrolysis, and this is where the mineral is changed by a reaction with water. So it isn't necessarily just dissolved, but it reacts with water and changes from one form to another. The most common process, or the most common example of this is silicate minerals turning into clays. So feldspars, for example, degrade into clays when they interact with water. A third is oxidation. This is basically rust. When an element loses an electron and the minerals involved change their form. So here we have an example of a car rusting out in the desert. This is metal being oxidized, but rocks also oxidize. So here we look at some granodiorite rock out in, this is in Anza Borrego Desert, east of San Diego. And what we're looking at here is, you see some of these rocks have more of a rusty color and then some are light. It's all the same rock material. It's just that the rusty surfaces have been exposed to the atmosphere longer. And then some of that material erodes off and gets moved away from this hill, and that exposes fresher rock underneath. The next picture, we're looking at an alluvial fan, and this is really obvious to see. The older fan has got this darker color to it because it's been exposed for a longer period of time and weathering. And whereas the active lobe is lighter, fresher rock that has not undergone as much weathering. Okay. So chemical weathering can occur at the surface. It can also occur a little bit below the surface. So this is an example explaining those formations that you see in Joshua Tree. So you start to get soil developing here, and weathering tends to form along planes of weakness, whether that's bedding planes or joints. In this case, we're looking at kind of granitic type rock that's full of joints. The water seeps down in there. It starts to decompose the silicate minerals and turning into clays, and then in this case later on it was washed away, and we're left with just the more solid intact part. So here's an example of a granitic rock undergoing weathering, again from Anza Borrego. So you can see these are joints, and this is where the weathering is intensified because this is a conduit for water to get down in there. So we're going to zoom in on one of these with my hammer for scale, and if you see this lighter colored material within these joints, this is clay forming. So again, this is granodiorite. It has some quartz in it. It has some plagioclase feldspar and some more mafic minerals, and the feldspars are breaking down and turning into clays. Okay, so there's various degrees of weathering, but again, it primarily occurs in the cracks and then propagates out from there. Now shifting to mechanical weathering. Mechanical weathering is where rocks are broken by some sort of force. And this can be gravity, it could be ice growing in the cracks. So the first type is what we call wedging. So this is where you have some sort of crack in the rock, water or gets down in there, and either it can freeze and turn into ice, and that expands and causes the rock to break apart, or that water might be precipitating salts, which also expand over time, and that causes the crack to be pushed apart and the rock starts to break apart. Okay, so below areas of mechanical weathering, you often see what we call talus slopes. So talus, another word is scree, S-C-R-E-E. It just means broken up rock fragments from a cliff above. So this stuff over time will just break off and build up at the base. Another type of mechanical weathering is changes in pressure. We get unloading. So as a rock moves somehow from deeper down to closer to the surface, either because the surface is being eroded or the thing is actually being brought up by a fault, say. The change in pressure from large confining pressure down at depth to basically zero at the surface causes the rock to expand, and you oftentimes see these sheets kind of coming off the rock that are more or less parallel to the landscape or the surface as it rises up towards the surface. So a good example, this is Half Dome in Yosemite, and you can see these sheets popping off from mechanical weathering, unloading. A third type would be thermal changes. You can have, as rocks get heated and cooled, they expand and contract, and you can repeat this over and over and over again, and it gradually breaks the rock up. Or this example from these mud volcanoes, you have hot mud erupting. It's also wet, so this isn't a perfect example, but as the mud cools, it then contracts and forms these cracks, similar to what you would see in a lava on Hawaii or something, where as it cools, it contracts and cracks into pieces. So this is contributing to weathering of that material. And the fourth one here, the last one, is weathering by animals or plants. So you've probably seen areas where roots are growing into cracks in the rock, and as those roots grow, that forces the rocks apart. Animals can also contribute to weathering in the same way, kind of gradually breaking rocks apart. And so how fast does weathering occur? Well, it depends on a variety of things, but the two most important are the climate and the rock type. So generally, more solid, harder rock will weather slower, and wetter climate will create weathering faster. But this really has a big, it really depends on both. So for example, limestones are very resistant to weathering in dry environments. So if you go out into Death Valley or the western US, limestones tend to make big ridges and more resistant areas. Whereas in a wetter climate, like the East Coast or the Midwest, limestones just completely dissolve, and so they tend to weather very fast. So it's the same rock type, but the climate is dictating how it weathers. Why am I showing a cemetery here? Because headstones are often made out of many different rock types, and they've been used in studies to measure weathering rates, because you have the date right on it. You don't have to date this rock, it's got a date right on it. So you have a headstone, it's got a date on here, 1903. We can see what type of rock it is, how long it's been there, and we can get a measurement of the weathering rate. You can compare one headstone might be made out of limestone and another one's made out of granite, and you can see the differences in those. Okay? So as rock breaks down, you create what's called a weathering profile. So the weathering starts at the surface and it gradually kind of propagates down into the rock. And over time, you start to develop very distinct zones. We call a soil profile or a weathering profile. So this is an example. At the top, there's a layer of grass, so that's obviously not derived from the rock. But then you'll have some organic soil. So this is a mixture of a lot of organic material with some mineral material. Below that, you have slightly more mineral material and less organics, and so on until you get down and the rock becomes more and more intact, until finally you get to the original parent rock that hasn't been broken down at all. So as rock breaks down, a weathering profile develops. We also call this a soil profile. Soil is a mixture of mineral and organic matter developed from the weathering. So this figure is really important, and I would stop the lecture here and try to redraw this. But I'm going to point out the key points. So these are different soil horizons, and there's a whole science to this, so this is a simplified version. But this figure has the most common and important parts of these, of a soil profile or weathering profile. So at the top you usually have what we call an O horizon. O stands for organic, and this is loose or partly decayed organic material. So in Southern California, the O horizons are very thin. There's not a whole lot of organic material. But if you were to take a hike outside of Seattle, for example, the forest is almost like spongy. It's like soft because you have a pretty thick buildup of organic material on the forest floor. Beneath that, you get what's called an A horizon. So the A horizon is a mixture of mineral material mixed with some humus, which is another term for decayed organic material. So this is sort of a mixture of the two. Below that, oftentimes you'll form what's called an E horizon. Now this is called a zone of leaching. This is where water is percolating down through the soil, and it picks up any type of material that is dissolvable. So this is typically clays. Well, clays aren't dissolvable, but fine-grained enough that they can move downward with the water, or calcium carbonate. So the E horizon is where that material is being leached out or taken out. And then just below that is the B horizon, and that's where that material is being deposited. So you're moving clays or calcium carbonate downward. So the net result is that you get sort of a bleached out looking layer, that's the E horizon, and then a B horizon tends to be more saturated with either clays or calcium carbonate. If it's clays, the B horizon takes on a very orange reddish tinge. The more clay, the more red it gets, the darker. If it's calcium carbonate, as in the case out in the desert, it takes on a whiter appearance. Okay, and then below that we call the C horizon. Is just where the rock's starting to break up. It's pretty much the parent material, but maybe the feldspars have decayed a little bit, so it's loose. It's not nearly as solid. And then you get down to the unweathered parent material. Okay, so these horizons are something to look at and study. O horizon, A horizon, E, B, C, and then unweathered parent material. Okay, so over time, these horizons will get more well-defined, and they'll oftentimes get a little bit thicker. So you can infer the relative age of a soil or a deposit by looking at how well developed this soil profile is. And on that second field trip, we'll look at a soil profile at Bolsa Chica and see an example. There, we don't see any E horizon, but you will see an O, A, and B horizon. Okay? So I'm going to show you a couple examples of some soils, and again, this is a huge science. I'm not going to go into all the different types, but soil scientists have actually assigned names to types of soils, just like geologists have names for rocks. And generally, again, they're dictated by the rock type and the climate. So just two examples here. In tropics, you often get a laterite, or what's called an oxisol, developing. So this tends to be, rapid weathering, and you have pretty thick soil horizons. So this is a road cut in Costa Rica. And so you see you got grass up top. This dark horizon is the O horizon. You have a slightly lighter color. This is the E. This is the zone of leaching. And then most of this red material is the B horizon. Okay, and it's red because it's oxidized and it's clays. And then down here is probably C, and the unweathered parent material is not exposed. And the unweathered parent material is basalt, volcanic rock. Okay? So to compare that, this is an example of a desert soil, what we call an aridisol. Looks very different. And here actually, this is the B horizon. And notice that instead of looking reddish like it did in the tropics, it looks white because it's not so much the clays that's being transported down, it's calcium carbonate. So as the water infiltrates down through the soil, it dissolves calcium carbonate from above and deposits it here in the B horizon. So these are oftentimes called calcic soils, and those B horizons, because they're made of calcium carbonate, they can become really lithified and hard. And this is oftentimes, this little layer is called a hard pan. So in desert environments, you get this hard pan developing. So, you know, when you're trying to bury a body out in the desert outside of Las Vegas and your shovel is, you know, stopping at about a foot deep, that's because you're hitting this hard pan. This is generally developing at about the depth that water seeps in during storms before it evaporates. Because the water is seeping down, picking up the calcium carbonate, and then it evaporates because you're in a desert environment, leaving that calcium carbonate behind. And once it starts to form, it's then an impermeable layer, so water just ponds on top of this, and it just is a feedback process, a runaway, and this develops even more and more. Okay. So there's maps of soil types, again, just like rocks. You know, this is an example from North and South America. I'm not going to go through it, but if you want to stop the video and take a look at this. So they have, again, names for different soils that are more or less dictated by the environment and the rock type. So as I mentioned a couple times now, soil formation is dependent on the climate and the rock type, the parent material. But obviously time is a big factor here. Over time, the soil develops more and more. The topography and the biology can also have an effect. So biology, I mean what kind of plants are growing there, what kind of animals are maybe helping move things around. You know, these burrowing rodents actually move a lot of material over time. But it's this fact that time is needed for a soil to develop that is really useful for geomorphologists, because we can use soils as a qualitative measure of the age of a deposit. Okay, and we'll see that again in a second here. And then soil erosion can be a problem in some places, and you know, because it's much softer than most parent material or hard rock. It's already decomposed and it's easy to move once you got water flowing over it. And so vegetation helps to hold the soil together. So anytime vegetation is wiped off, whether it's you know, bad practices in farming in the Midwest, you know, you get soil erosion, stripping of the soils over time. In Southern California, our fires in the mountains oftentimes cause a lot of soil erosion and stripping of the vegetation from the fire. Then you kill the roots, and then that allows the soil to move down slope. So here what we're looking at is a fire in the mountains of Orange County, and maybe you can see this is a little scarp forming as a landslide starts to occur. So the vegetation was stripped off, and so the soil is now loose and it's coming down the mountain. Soil can also be removed by high winds. So many places where you see farms, you know, they'll plant these rows of trees, and the whole point of this is to act as a windbreak, to try to prevent the wind from picking loose soil up and removing it. So as I mentioned before, one really cool thing about soils is they can be used as a form of relative dating. So for example, if I have several different fluvial terraces in a mountain range and different drainages, and I want to know if they are the same age or not, one way I can do that is I describe the soils on a terrace in one drainage and on a terrace in another drainage. And I can compare those, and if I see that they are the same degree of development, I can assume that these are roughly the same age. And then if I was to actually get numeric dates on one set of terraces, I can use soil correlations to extrapolate those numeric ages to other locations without having to get numeric dates from each spot. I can do it in one spot and then compare that and understand the ages of deposits over a much wider area. Okay. In fault studies, these soils are often helpful, not only because they can be relative age markers, but because they show paleo surfaces, or the paleo surface of the soil. So for example, in this picture, what we're looking at is, here's a fault, and imagine this is a cross section, maybe a trench or a road cut. So there are buried soils in the deposit. So each one of these buried soils is representing a time when this was at the surface. So what that means is that we see a soil here. That means that this sat at the surface for a while, and enough for weathering to occur and soil to develop, but then the next earthquake occurred on the fault and it dropped that soil down. And now this is at the surface, and so a soil starts to develop there. The next earthquake drops that down. So the recognition of these old buried soils is basically giving us a record of the earthquakes along this fault and showing repeated earthquakes. So if you stop the video and look at this a little closer, this is showing a time progression of that occurring along a fault. So you have a soil here, then an earthquake comes and drops soil A, and then B gets deposited and it sits there for a while. A new soil develops, then it gets dropped again by another earthquake, and so on. Okay. So these soils can be helpful for a variety of different things. They can tell us something about paleoclimate in some cases, relative age, or in this case, something about the tectonics. Okay. So I'm going to stop the lecture there, and I will see you guys on Friday.